All right, so topic for this week is infinite sequences and series. And this topic is actually going to take us about 4 weeks to play with. It's a pretty big one. A sequence is just a list of numbers. And even better, it's an ordered list of numbers. Oftentimes, we'll write a sequence in curly brackets because it's also a set, but the order matters. So the most basic sequence of all is our counting numbers, 1, 2, 3, 4, and so on, forever and ever. And sometimes we might say there's an nth one. Another common sequence would be even numbers. You start learning to count by 2 way back in kindergarten or sooner. 2, 4, 6. And if we were going to write an algebraic formula for this, given that there is a first element, a second element, a third element, eventually there'll be an nth element. What might I call that nth element? Excellent, 2n. It's Monday for all of us. All right, and that list can go on forever and ever. So you've played with sequences before. We used sequences when we were doing calculus, a little bit in calculus 1, but mostly in calculus 2 when we're playing around with Riemann sums. The idea of a series is a little bit different. A series is a sum. Now, generally, we're summing up a whole bunch of things. So we're summing up a sequence. So in a lot of technology, to do a series, you'll do something like sum a sequence. Okay. Now, it's going to get more exciting a little later. Consider the sequence x, let's throw a 1 in there too, and then x squared, and then x cubed. I could sum that sequence by saying that's 1 plus x squared plus x cubed. And that's commonly known as polynomial, right? So you've been doing sequences and series forever. We just don't usually call them that way. So this particular one is called a polynomial. Wouldn't it be interesting if we could have infinitely long polynomials? Polynomials that never ended. And it turns out you can. Okay, and they are known as power series. So this is where we're going to work our way up to at the end of this unit, the idea of power series. So power series could be something like 1 plus x squared plus x cubed, and then it just keeps on going forever. Eventually there'll be an nth term, and then it doesn't stop there. It goes forever and ever. And then the question is, can this actually be a function of x? Or will it just be this infinite blob of weirdness that's we can't do anything with? Well, yes, the answer to the question is it's going to be something interesting. Otherwise, why the heck would we study it, right? So it turns out these are going to be very useful functions. They're going to be super powerful in a lot of areas. And like integration introduced us to functions we didn't know existed, power series are going to introduce us to functions that we didn't know existed prior to this. Okay. they come up in a lot of places. One place they come up is in terms of waves. We'll see them. You remember the crazy SI function when we tried to integrate sine of x divided by x and we couldn't get anywhere? And one way to explore it was with Riemann sum, which was rather tedious. Turns out there's a rather nice power series for that function that's way easier than the Riemann sum. Power series are going to open up a whole new world of stuff for us, which are kind of wild. So before we can get to power series, we got to get a handle on series. Before we can get a handle on series, we got to get a handle on sequences. So today we're going to start with sequences, and we're going to work our way up to that. Kind of an interesting lead to the infinite series. Think of the function y equals e to the x. Okay. What's y prime? It's e to the x. And what's y double prime? It's e to the x too, right? It's the same derivative over and over again. Oops, e to the x. Interesting thing is if we say, hey, what's the tangent line of e to the x when x equals 0, y equals 1? The tangent line is just going to be y equals x plus 1. So if you were to graph e to the x, the graph is going to look something like this. And there's going to be this cute little tangent line right there that has a slope of 1. And tangent lines are nice because we can use them for approximations, because how do you calculate E anyway? Right? We could say it's about 2.7, but that's not very accurate. And so tangent lines allow us to get an approximation near a particular x value. The problem is that tangent line loses its ability to approximate later on, right? It gets less and less accurate. Wouldn't it be awesome if we could have a tangent parabola? Because the nice thing about tangent parabolas is they have concavity. And so it turns out you could, and we're going to test this out with your graphing calculator in just a second. You could have at the point 0, 1, parabola is y equals 1/2 x squared plus x plus 1. Let's take a look at that, see what it looks like. I think I got the right one. Let's go to a new screen where I haven't destroyed something. Desmos e raised to the x. And then I'm going to zoom in at that point right there. And then my claim was that x plus 1 was a nice tangent line, which it is. And now my claim is that if we add on to this 1/2 x squared, then we get a lovely tangent parabola in there. And when you zoom in on there, it's really hard to tell the difference between the two. They're really tight for a while compared to the tangent line, x plus 1, which loses its ability to approximate quite quickly. Okay. But then you might ask, well, tangent parabolas are awesome, but why stop there? Why not have a tangent cubic? Or a tangent 4th power function? Or a tangent 5th power, 6th power? Wait a minute. Is it possible to represent e to the x as one of these, let their page go, as one of these polynomials? And the trick is, if we can pick the coefficients in front right, we can do so. Okay. So I'm going to extend this guy just a little bit and see what happens to it. So we'll come back to e to the x later. Let's turn these guys off. So if I look at 1 plus x, I get that function, plus x squared, all right, plus x cubed. Oops, something went wrong there. That was bizarre. X cubed. All right, can I keep going? Plus x to the 4th. I'm just going to add a whole bunch of these, plus x raised to the 5th. It'd be nice to have a sequence generator here. Plus x to the, where am I, 6th. Ooh, something's happening in there. Plus x raised to the 7th. Notice they're all kind of behaving the same way near 0, 1. Plus x raised to the 8th. Plus x raised to the 9th. This game kind of tedious, isn't it? X raised to the 10th. they're all starting to behave the same way in the middle here. So the more terms I take out, the more they're behaving the same around the 0.01. So in Calc 1 and 2, we studied the idea of limiting processes. What happens in the limit as we keep exploring this? And so what we're seeing here is that in the limit, it's starting to take hold of some interesting shape there. And so we're going to take a look at studying that a little bit later. So we're going to discover new ways to represent old functions and new functions that we never knew before. All right, getting used to sequences. So important things again about sequences is that a sequence is an ordered list. And it's nice to have technology to help you with an ordered list. Spreadsheets are awesome for playing with sequences and series. They make it super easy. GeoGebra is not too bad playing with sequences and series. We just spent a few minutes before the video started playing with Desmos, and apparently it is not easy to play with sequences in Desmos, but we'll give it a try soon anyway. So basic ordered lists, some things to consider. I'm going to put this in a table form. And I'm going to pick on that really easy one, 2n. So when we count a sequence, so for example, I have a first term that's going to be 2, I have a second term that's 4, I have a third term that's 6, and so on. The number that we count with, whether we call it n or I or something else, that's called the index of the terms. So 3 here is the index. The 6 is known as a term in the sequence. So you might remember back from algebra, you talked about like terms, right? 1 and 2 are like terms, you can add them and get 3. 1 and x are not like terms because you can add them and you're stuck with 1 plus x. But 2x and x are like terms, you can add them and simplify them. So terms are just pieces of addition problems, which eventually that's what these guys are going to be when we look at series. For now, these terms are just numbers in a list. Okay, so we have our index and we have our actual term. Eventually, what we like to be able to do is identify a formula for the nth term. And sometimes those formulas are easy to come up with, sometimes they're not so easy to come up with. So here, n, the formula is just 2n, which I stated in the beginning anyway. A lot of times what we'll do is we'll give sequences names. And so we'll say, hey, this is sequence E. And then we'll put a little subscripted n next to it. So when you see the subscript, E represents some list, n represents the nth term in that list. Okay? So for example, I might write, what is E sub 3? Well, we'd look for list E, find the third term, and we would say it is 6. Okay? So we're going to use subscripts a lot to reference positions in the list. And we're always going to hope to find an nth term formula. And those formulas come in a couple of different ways. One form is this right here. This kind of formula is called an explicit formula. Explicit formulas provide immediate gratification. Okay, so let's find a formula that does not provide immediate gratification. Consider the sequence 1, 2, 3. Can you guess what's next? It's a trick question. Ooh, Clint, right at 5 was next. What's after that? That's what I wanted to be next. Good job. 8 is what I want to be next. Okay, someone besides Clint he's smoking hot today. He's on a roll. What could be next after 8? There's a voice in my head screaming 13, so I'm going to let it out and see if someone else can come with the term after that. So for example, if I called this sequence F right here, Clint discovered that F sub 4 was equal to 5, and then he said F sub 5 was 8, and then I blurted out, because I couldn't control myself, that F sub 6 was 13. So the next guy here is going to be the 7th term, right, F sub 7. And eventually what I'd like to do is I'd like to be able to come up with an nth term formula for this list of numbers. I picked F for a reason. Do you know why? Do you know what F stands for, Clint? No? Okay. I used to have a poster of it in this room, but it's missing. Okay, so here's the trick. 1 plus 2 is 3. 2 plus 3, 5. 3 plus 5, 8. 5 plus 8, 13. 8 plus 13 would be 21, so that's the next term. So how would I describe this? Well, if n is the position I want to be in, this one right here, I would take the term before it. So counting, if this is the nth term, what would we call the term right before n? The n minus 1th term, and the term before that one we also need. That would be n minus 2. So what we'd say is to generate the nth term, we take the term before that, n minus 1, and we add to that the term before that, which would be n minus 2. So we have to refer to two previous terms. Super important. You also, if you give a previous term to generate the sequence, then you got to tell somebody where to start. So I can't say this right here is the formula, because that generates a lot of different sequences. I also have to say, oh, by the way, the first term is 1 and the second term is 2. If I had referenced 3 previous terms, then I would have to give somebody the first 3 terms, otherwise they wouldn't know where to start. Okay. If I only needed to reference the first term, then I only need to reference, if I only needed to reference 1 term, then the first term is sufficient. So for example, that even sequence we were looking at a minute ago, I could say here that E sub n is equal to the previous term plus 2. That would be another way to describe this sequence. And if you asked like a first or second grader to describe this pattern, they probably wouldn't say it's 2n. What they would say is, oh, I just add 2 to get the next number, right? They would recognize this version in their head way before, because we have to train ourselves to learn algebra. But naturally, we recognize these kinds of patterns. We would also have to say, start, the first term of 2. This type of formula right here is not explicit. This is called a recursive formula. Recursive formulas depend on previous terms to generate them. And I mentioned this is not an immediate gratification formula, because what if I said, oh, by the way, please give me the 100th term in this sequence? Well, that means I need to know the 99th and the 98th. I don't know those, because they require the 98th and the 97th and the 96th and the 97th and 95th and 96th and so on. So to generate the sequence, you need to know every single term before where you're at. It's not immediate gratification. It means you have a lot of work to do. Okay. One reason I mentioned spreadsheets are nice ways to attack this is spreadsheets are really good at reviewing previous terms. So just come here. There you go. So I'm just going to bring up my Google Sheets for a minute. Drive first, and calculus, and make a new sheet. And so a lot of times when I'm doing sequences and series before variables, I'll play around here. So I may make a column for n, and then any particular one. And I usually will list out 1, 2, 3, 4, but that's really not necessary. Because here, my even number started at 2. And then a kid might recognize, oh yeah, just add 2 to that. So take the previous term plus 2. And spreadsheets use what are called relative cell referencing. So then I can just click on that cell and then fill it down. and it will always just take the cell above and add 2 to it. And I don't even need these references over here, but I got them there. I mentioned earlier that just knowing the recursion part of the formula isn't enough. You have to know where to start, because there are many sequences that have this pattern, and there are many sequences that have this pattern. For example, where's my spreadsheet? Here we go. I'm going to call this sequence O, and I'm going to start at 1, and then I'm going to take that number and add 2 to it to get the next term. So I'm using that same pattern, add 2 to the previous term, but it generates a whole new list of numbers. That's not what I have here. So just something to keep in mind when we're generating sequence and series. Anytime we do it recursively, we must have previous terms listed. Okay. So recursive formulas require starting terms. Okay. And we need as many terms as we have references in the formula. All right, so for example, I had that recursive formula f sub n was equal to f sub n minus 1 plus f sub n minus 2. And let's suppose here I say, well, let's let the first term be 1, and let's let the second term be 1 also. So to get the third term, the formula says take whatever n minus 1 is, well, that would be 3 minus 1 is 2, and add that to 3 minus 2 would be 1. Well, for me, that's just 1 plus 1, and so there's my 2. The fourth term, according to this relationship here, would be the term before that, which would be the third term plus the second term. And so that would be the third term is a 2, the second term was a 1, so then I get a 3. And this notation is cumbersome, but unfortunately it's really necessary to describe these sometimes. Often I'll just list out the numbers after 1, 1, 2, 3, and then we know what happens from there. Now this happened to give the same list of numbers I had before with just a different starting point. And these numbers, I used F because they're called Fibonacci numbers. And Fibonacci numbers come up in a variety of ways. They're related to reproduction in certain animals like bees and rabbits and possibly humans if we force reproductive principles on them. It also comes up in patterns like the way spirals go and seeds form on certain flowers. So there's a lot of cool things about them. Fibonacci numbers are also related to the golden ratio, which is kind of wild. Now notice I haven't given an explicit formula for this because it is rather tedious. And so I'm just going to go to the internet and see what the internet has on Fibonacci. There we go. And Wikipedia says, hey, how about Fibonacci numbers? And they're giving this interesting picture here, which requires some explanation, but what I'm hoping is they'll list the closed form expression. Oh yeah, look at that. Interesting. So here they're giving a formula for the nth term in terms of these numbers, phi and psi. And phi is 1 plus the square root of 5 over 2, which is the golden ratio, and psi is 1 minus the square root of 5 over 2. Notice that they have powers of n to them. Okay, so and this is rather hard to calculate, but it's doable in about a half an hour. We're just not going to take that half an hour today. So according to the Wikipedia site, another way to generate f sub n would be to take 1 plus the square root of 5 over 2 to the power n minus parentheses 1 minus the square root of 5 over 2 to the power n, and divide all of that by the square root of 5. So that's the closed or explicit formula versus, so again, that's explicit. The recursive formula is take the term before it, add it to 2 terms before, oops, starting with a first term of 1 and a second term of 1. If you pick other starting terms, then you get a variation of this guy up here, not quite the same. The golden ratio will still be involved. Okay. And again, this is called a recursive formula here. There are some functions for which the recursive formula is easier than the closed formula, in this case right here. There are others for which the closed form is easier than the recursive. There are some functions for which a explicit formula, it's also called a closed formula, by the way. You'll hear me use the term closed often. For which a recursive formula is not that bad to come up with, but it's impossible or incredibly difficult to come up with an explicit formula. It might not exist sometimes. But usually for most common things, they'll exist together, and they're not too much more difficult than each other, except in some circumstances like this. Mostly what we're hoping for is we are hoping more often than not to find an explicit formula, because then we can use it for limits. Can you use recursive formulas in limits? Turns out you can use them in limits too. It's just a little trickier, and we'll apply that later. All right, let's try some other ones. So I'm going to list some formulas. I want you to try and come up with patterns for me. So how about 1? I want to start with 1. Oh, sure, fine. 1, 3, 9, 27. What's next? Three to the fourth or 81? Yeah, excellent. Yeah, 3 to the 4th power. Yeah, so pattern here is that to get from here to here, in my head, I multiplied by 3. And then I multiplied by 3 again. And then I multiplied by 3 again. And if we get here, then we would multiply by 3 again, okay, to get that one. And we just keep that pattern. So I could write, based on the way I was deriving it in my head, I was thinking, okay, I'm going to call this sequence A sub n, and A sub n was 3 times the previous term, A sub n minus 1. Now that right there on its own isn't enough to generate this sequence, because that right there could generate the sequence 2, 6, 18, 54. I also would have to state, oh, by the way, please start at 1. Whereas the one down below, let's call that B, B sub n is also 3 times the previous term, B sub n minus 1. But here, I started with a first term of 2. Right? So with recursive formulas, we have to have a starting place. All right, so here's the challenge next. With this sequence right here, I have to make a note that this is the first term, that's the second, that's the third, that's the fourth, that one's the fifth. What I would like, instead of a recursive formula, I would like a closed formula for the nth term of this sequence. 3 to the power n, okay. So double check. To get the 4th term here, I would take 3 to the 4th power, which gives me 81, not 27. So you're close. How could we tweak it? Minus 1 up here? Like that? Yeah. Yeah, so drop the power by 1. Because note, here's the trick. started at 1. And I only multiplied to jump to the next term. Okay. So here's, I have to take out the fact that I started at 1 and then started multiplying by 3 after. Okay, so there's that little catch there. So types of sequences like that have repeated multiplication, these are called geometric sequences. And they are powerful and popular. We'll come back to them. Let's try another one. How about color and new page? Let's say 3 and then 7. And then how about 11 and 15? What could be the next term in my sequence? 19? Excellent. I was thinking 19 would be a good number to have next. Okay. And how did you discover that? Yeah, add 4. So if we look at this and we say, oh, add 4, add 4, add 4, add 4 over and over again, then we could say the formula, let's call this C sub n, would be the previous term, C sub n minus 1 times 4. Plus 4, oops, sorry, times with the last page. Note, I should probably say, hey, by the way, please start with the first term of 3, because otherwise this could make other lists. So for example, if instead someone said, no, I want to start at 1, then I would have the list 1, 5, 9, 13, a very different list of numbers, but they all have a similar pattern. The pattern is that each number here is 4 apart. Okay, so it still has the same recurrence relation. C sub n still is equal to 4 plus C sub n minus 1, but we have a different starting point. These types of lists where the numbers are all the same distance apart, these are called arithmetic, which looks just like arithmetic, but for some reason we have to pronounce it differently in this chapter. Arithmetic sequences. Oops. Ooh, and did I lie and call that a series last time? Oh no, I called it a sequence, good. Yeah, generally we're supposed to use the word sequence for a list and series when we start adding up that list. Okay, so let's have some more fun. I'm gonna whip out my spreadsheet for this fun, but it works just as well on paper. And let's see, let's give this a title, sequences. Oh, I skipped over explicit on those guys. Yeah, let's do an explicit. All right, so here I have repeated addition, correct? Repeated addition is typically written as multiplication, right? So, so the formula for the nth term, hopping on down the line, we get to position n here, it should have something to do with 4 times n. So we check that. This is the first term, second term, third term, fourth term, fifth term. 5 times 4 is what? 20. That's a touch too big. Ooh, yeah, that's a touch too big, right? I want it to be a little smaller, so I should do what to this? Take 1 away from it after. Test it on the previous one. 4 times 4 is 16, minus 1 is 15. Hey, that works fine. Will that same formula work down here? Answer is no, it won't work the same because we have a different starting point. Okay, but aren't we repeatedly adding 4? So the nth term, explicit, again, this one is explicit. Explicit. And in the homework, pay attention whether it asks for an explicit formula or recursive. Here, for an explicit formula, we're still going to have a 4n. Testing that out, let's test it on turn number 2. 4 times 2 is 10? No. 8 on 8. 4 times 5 is 10. Okay, sorry. 4 times 2 is 8. I want it to be 5. So if we take 3 away from that, so then we test it on a later one, like the fourth one, 4 times 4 is 16, minus 3 is 13. Okay, check. So we can do kind of a guess and check there. Another way to think about that one that's kind of like the geometric stuff we looked at a minute ago. Somebody might note that, well, really what happened here is we started with 1 down here, right? And then we started adding up a whole bunch of 4s. How many 4s did we add? Well, to get to the 4th place, I only made 1, 2, 3 jumps. So in general, I'm going to make 1 less jump than where I'm at because I had some place to start. I was already at position number 1. Okay, so we could write that up here too. This one would be starting at 3, add a bunch of 4s. How many 4s should I add? Well, I already have the first one, so it's always 1 less jump than where I'm at because I started at place 1. And if you multiply that out to double check, you're going to get 3 plus 4n minus 4. 3 minus 4 is minus 1, so it does check out. So there's multiple ways to think about these formulas. But we could either have a recursive formula like this or an explicit formula like that. All right, let's see. What was I going to do next? I had an idea. Oh, that's in the wrong spot. Let me go back there somewhere. Oh gosh, all these are out of place. Clean them up later. Oh no, that's where it's supposed to be, yes. Okay. I had a thought of what to do next. I guess I better look at my notes. Oh yeah, that's a cute one. Okay. I'm just going to give you a formula. Let's run out of letters and go back to A. Let's say A sub n is going to be equal to negative 1 over n. No, let's do, ooh, I know, negative 1/2 to the nth power. So is this formula explicit or recursive? It is explicit because I can get immediate gratification. It doesn't reference previous terms, okay? So then I can generate a table for this guy right here. So I can say, all right, here's n, here's a sub n. If n is 1, well, I just get negative 1/2. If n is 2, negative times negative is a positive 1/4. If n is 3, negative 1/8. If n is 4, positive 1/16. So cool thing about this sequence, it is alternating. Anytime I have an odd power, I'm going to get a negative number. Even powers lead to a positive number. And this one's kind of hard to graph because it's going to disintegrate pretty quickly here. But if we put, let's say my negative 1/2 is way down here. And so positive 1/4 would be about right there. That's a 1/4 and 1/8 would be about here. And then it's getting harder and harder to graph. So 1/4 and 1/8, 16th, and 16th, 32nd. 1, 2, 3, 4, 5. So graphing this sequence, we usually let this axis here be the n-axis, and this is the answer axis. So we get the point 1, negative 1/8, and we get the point, oh, 1/2. Oops, why did I do that? Negative 1/2, there we go. And then 1/4, and then negative 1/8, and then positive 1/16, negative 1/32. So we can see it bouncing around, and it's going to start hugging the axis pretty tight, and it's going to get harder and harder to see here. It's kind of disappear from view. We could connect the dots. It's not usually that important to do so. And then it's just going to be this wiggly blur on the axis after that. Okay. Some things we're going to start looking at more closely tomorrow is the idea is, well, what's the limit as n gets big for a particular sequence? And sometimes we're going to find that there is a limit. Like, what do you think the limit here is going to be for this particular sequence? It's heading to 0, right? It's positive, negative, but ultimately it's going to 0. So we can show that based on previous laws of limits that we worked with. Now, keep in mind, when we worked with limits before, we took limits of continuous functions as x did something. And the rules of discrete functions is when you have countable things. Continuous is where you have a smooth line. The rules about continuous stuff and discrete stuff are pretty darn near the same. So all the rules we knew about limits before apply now. Any limit we knew for a continuous function is going to help us analyzing these discrete functions here, okay? Because it's just a subset of the points from the continuous one. We only care about when x was a whole number, right? So we've learned a lot of stuff that's going to help us out. So we're about out of time for fun with math today. Hopefully tonight I will master how to use Desmos and help you out with it. Based on my first try with Desmos, my guess is GeoGebra does a way easier job with sequences. And we're just going to play around with some graphs of sequences. Tomorrow we're going to get more into the theory of limits, when they exist, when they don't. And then we're going to start adding stuff up, will be the next stage. Again, I won't be here on Thursday. I'm going to be in transit to the conference, so I'm not going to be able to do a live recording then, but there's plenty of good videos on our website. So on Wednesday, we'll discuss what I think you should be doing on Thursday without me around. But most likely, I'll have you set up pretty good Wednesday for Thursday's work.